Hi everyone, and welcome to our next lesson in chemistry. And we're changing chapters, and we're changing subjects a little bit. And we're going to introduce this idea of stoichiometry. And so you can see here that I've spelled it out phonetically: stoichiometry. And this is an important concept that you're going to need in chemistry moving forward. And so we're going to take about a week to go over stoichiometry from different perspectives. And today is the first lesson where I'm going to expose you to it. And what stoichiometry deals with are the basically, it's the relationships that the balanced chemical equation gives us. And so I've defined it here as stoichiometry is the quantitative relationship among the reactants and products. And so when we hear that term quantitative, what we mean is numbers, the numbers involved. So, how many or how much of each are we going to use? And just out of interest, the term stoichiometry is derived from two Greek words, stoichion, meaning element, and metron, meaning measure. So a measure of the elements, okay, is a measure of the elements. And one thing I'll say is that the starting point of stoichiometry is a balanced chemical equation. That is what is going to help us in this next little bit, is using a balanced chemical equation, and what does it mean? Okay, well, let's start with an analogy. And I really like this one. I found this one in a book, and I thought it was a really good one. Basically, this is an analogy about building a bike. And so really what we have here is an equation for building a bike. And watch this, I'm going to add in an arrow here so it looks like a chemical equation. And then I'm going to put here the word bike. So this is like a synthesis equation because we're taking a bunch of smaller things and creating one thing. So if you are able to take two wheels, one body, one handlebar, and one gear chain, and again, I know I've simplified a bike, but those things are required. When they combine, you will make a bike. And so that's an analogy for a chemical equation. Well, essentially, they've given you the recipe, and the recipe says, and it's all about quantities here. I want to emphasize this because in tomorrow's lesson, I'm going to talk about masses, whereas today all I'm going to talk about is counts. So if you have a count of two wheels, if you have one body or one frame, let's call it, if you have one handlebar and you have one gear chain, you can make one bike. So it's all about the counts. Those are the counts that you need to make a bike. Okay, well, this would be a typical question in stoichiometry. It says, well, how many bikes can you produce if you're given 8 wheels, 5 bodies, 6 handlebars, and 5 gear chains? Well, you've got to look back at your equation, and that's going to tell you. And so they've shown them here as pictures, but there are your 8 wheels, there are your 5 bodies, there are your 6 handlebars, and there are your 5 gear chains. Well, someone may say right off the bat, well, you can only make 5 bikes, and you may be right. But what I'm going to tell you is that you need to look at the number of parts you have and how much are being used in each bike. So let's take a look at the answer here. And the answer shows that you can actually only make 4 bikes. Okay, so look at this, you can only make 4. And the reason is that because each bike uses 2 wheels, that essentially for the first bike, we use that wheel and that wheel, we use that frame or body, we use that handlebar, and we use that gear chain. So those things together made a bike. And so we did the same thing again, those two, and so on. We made the second bike, those two. We made the third bike, those two. And that one we made the fourth bike. So notice that the tires ran out, or the wheels ran out. And so notice that we actually have left over, we have a frame left over, we have two handlebars left over, and we have a gear chain left over. Those things are left over because we didn't have enough of the rest of the parts. And this is what stoichiometry is about, is understanding how the balanced chemical equation is used to show you how much you can make of something. Okay, so that's an analogy. Well, let's now get back to chemistry, and let's look at the meaning of a balanced chemical equation. Let's remind ourselves of this, and I think this is really important, this slide. And so right off the bat, it says that here's the chemical equation, and again in unit 2 we learned how to balance chemical equations. So one in this case N2, one molecule of N2 plus 3 molecules of H2, and look at that MOLC is a short form for molecule. I'm just going to write that up here. I know that's a kind of a funny looking thing. That technically means molecule. Okay, so 1 molecule of N2 plus 3 molecules of H2 makes 2 molecules of NH3. Don't worry about the double arrows. Again, it essentially means that the equation can move back and forth, but we're not that worried about it. Okay, so here it is. That's what notice the equation is all about counts. It's not about mass, it's about counts. 1 molecule plus 3 molecules makes 2 molecules. Now, interestingly, even though those don't seem to add up, like people will say, well, 1 plus 3 doesn't equal 2, we actually don't care about the number of molecules, we care about the number of atoms, and sure enough, the number of atoms does add up. Okay, well, let's look at it from another perspective. If we had 10 molecules of N2, we would need 30 molecules of H2, and we would make 20 molecules of NH3. You can scale this up. Okay, let's look at it another way. Oh, you could have 100 molecules of N2 and then 300 molecules of H2 to make 200 molecules of NH3. Okay, we're going to go even bigger now. 1 trillion molecules of H2. You'd need 3 trillion molecules of H2 to make 2 trillion molecules. It's all about counts. Okay? And then here, this is a funny number. It's much bigger than 1 trillion, but you guys will recognize it. It's Avogadro's number. And it says here that if you had 1 times Avogadro's number, 6.02 times 10 to the 23 molecules of N2, you would need 3 times that of H2 and to make 2 times that number of NH3. But again, we've picked that number in particular because of something important. And that is, we know that that's the number of particles in a mole. So basically, here's the key, is that we know that if you have 1 mole, that's 1 times 6.02 times 10 to the 23, if you have 1 mole of N2 and 3 moles of H2, you can make 2 moles. So really, your balanced equation, your balanced chemical equation tells you the moles required, okay? And remember, the term mole just replaces a number. It's like a dozen, but instead of it being 12, it's this really big number here, this 6.02 times 10 to the 23. Okay, so that tells you, this shows you a few pictures of what we're talking about here. It's just the number of showing it to you from a pictorial standpoint. Okay, so once again, let me emphasize that once you have a balanced equation, you know the number of moles of each of them you need, but you also know the molecules of each of them that you need. Now, the molecules are tiny, the moles are quite large. All right, well, let's try a question. So this is similar to one of your homework questions, and it says, Iron reacts with chlorine gas to form iron 3 chloride, and they gave you the balanced chemical equation. So I'm going to come down here and I'm going to write that equation again just to have it with me. And I recommend that most of these questions you start by rewriting your chemical equation. It's the key as we do these. Okay, so let's read the first, part A. It says, how many atoms of Fe, so I'm going to put a little question mark there, how many atoms of Fe are needed to react with 3 molecules of Cl2? Okay, so look at this. We're given that we've got 3 molecules of this. How many of them are you going to need to react? All right, well, what I do is I'm going to set up a ratio. And watch this, I always go to my balanced chemical equation to set up my ratio. So here we go. The question has asked me about Fe, so I'm going to put Fe right here. And I'm going to compare it because they've given me something about the Cl2. They didn't give me anything about the FeCl3, so I'm going to ignore it. But they gave me something about the Cl2. And so I'm going to write a ratio. And I always know one ratio because I've got my balanced equation. So watch this. 2 Fe's are required for 3. I got that from my balanced equation. Every time you use 2 Fe's, you need 3 of the Cl2s. Okay, well then look what I'm going to do. I'm now going to write another ratio for my unknowns. And so in this case, they were trying to solve for the number of atoms of Fe, so I'm going to make that X, I don't know that, are required for 3 molecules of Cl2. Well, a lot of you are going to look at that and say, well, that's a pretty easy ratio to solve, Mr. Webster, and it is. You can see that obviously in this situation, I would need 2 atoms of Fe. And again, that was an easy question because it was the exact same as your balanced chemical equation. Let's try one that's maybe not quite as easy. So that was A. Let's try B. Okay, so B says, how many molecules of FeCl3? So now we're looking over here. How many of these? So I'm going to put a little, here I'm going to change the color of my pen. So I'm going to say, okay, for that, how many of those are needed to react with, are formed when 150 atoms of Fe react with sufficient Cl2. Now, they put that in there just to say, don't worry about the Cl2. But here it is. The key is they've put the 150 with the Fe. So now we've been given 150 of the Fe. Well, you always start with your ratio. So look at this. I'm going to do a ratio of Fe, in this case now, to FeCl3. The reason why I'm doing it, because that's the one I've been given something about. I've been given that I have 150 of them, and this is the one that I'm trying to solve for. Okay, well, I always start by writing the ratio that's given to me in the equation. So look at this. I'm going to use the 2 here, that's in the balanced equation, and I'm going to use the 2 here because that's the balanced equation. So it's a 2 to 2. It's an even ratio. So I need the exact same amount of Fe as I will produce FeCl3. That's kind of nice. Okay. So, but look, it told me in the question I have 150 atoms of the Fe and an unknown amount of FeCl3. That's my unknown. So again, we don't need to cross multiply or anything in this to solve this ratio. We can just see, well, if it's a 2 to 2 ratio, in other words, the same number is on the top and the bottom, then X clearly here must be the same number as the top and the bottom. So it's 150. Okay. So we know that if we have 150 atoms of the Fe, we will produce 150 of the FeCl3. Okay, let's try another one. C. So here we go. C says, how many Cl2 molecules are needed to react with, oh, we got a really big number this time. How many of those are needed to react? So here, my question mark now is here. and how many of those are needed to react with, and instead of 150, we've got 1.204 times 10 to the 24. Okay, so notice that this question asks nothing about the FeCl3, so I'm once again going to come back here and I'm going to go my ratio of Fe to Cl2. From the balanced equation, I know that it's a 2 to 3 ratio, but look at this. Now I've been told that I've got 1.204 times 10 to the 24 over x. So what's my x? Well, the ratio tells me it's 2 to 3. Now, what I'm going to show you is an easy way to solve ratios, and I haven't had to do it in the first two because they were easy ratios. But watch what I'm going to cross multiply here. So look at this. I'm going to multiply my x up there, and I'm going to multiply my 3 up here. So that'll give me 2x is equal to 3 times 1.204 times 10 to the 24. And then I want to get x by itself, so I'm going to get rid of the 2 by dividing by 2. So that's kind of cross multiplying. And so now I'll grab my calculator, and you guys can do this with me, is you go 3 times 1.204. It's times 10, so on my calculator I hit EXP, and then I type in 24. That's times 10 to the 24 equals, my calculator says 3.612 times 10 to the 24, and then I'm going to divide by 2. Okay, so my final answer here is 1.806 times 10 to the 24. So that's how many molecules of Cl2 would be required. And you can kind of, it makes sense. It's going to be greater than the 1.2 because I know that 3 is greater than 2. So I'm feeling good about that number. Okay, let's do one more here, D. And D says, how many molecules of FeCl3 are formed when that number of the molecules of Cl2 react with sufficient Fe? So this one, we don't care about Fe. It's not a problem. We're worried about Cl2 and FeCl3. Okay, so here we go. I'm going to set up my ratio. So here's D. I'm going to go, well, I care about Cl2 and FeCl3. I go to my balanced equation to write my ratio. You always have one ratio, so it's a 3 to 2. So it's 3 of these to 2, and it doesn't matter which one you write on the top and bottom. I often get asked that by students. Does it matter if I put FeCl3 on top? It doesn't. It doesn't matter as long as you put these in the right place. So there are 3 Cl2s in the balanced equation, 2 FeCl3s, but the question tells me I've got 1.806 times 10 to the 24 molecules of Cl2, 1.806 times 10 to the 24 over x. Okay, so just double check that. I've been given that number of the Cl2. Beautiful. Okay, so now I cross multiply. So multiply the x up and the 2 up, and you get 3x is equal to 1.806 times 10 to the 24 times 2. So there's the 2 there, there's the 3 there, and then divide by 3 to get your x. I go to my calculator, I go 1.806 times 10 to the 24. It just happens to be in my calculator, so I'm just going to multiply it by 2, and then I'm going to divide by 3. And so here I get 1.204 times 10 to the 24. Okay, so that's using stoichiometry, you guys. It's using stoichiometry to solve questions. Let's try another question here. Okay, number 6. Ethane gas is present in small amounts in natural gas. It undergoes complete combustion, and it gives me the equation. So I'm going to rewrite the equation. 2C2H6 plus 7O2 makes 4CO2 plus 6H2O. Okay, It says how many moles of O2, we're doing A, so look at this, I'm going to put a question mark under O2. How many moles of O2 are required to react with 13.9 moles of C2H6? So look at this. I'm going to write here, I've been given 13.9 moles of this. And notice that I used my little n here because that's our symbol for moles. And look, they've asked me to solve for the moles of the O2. Now we know that we can use the ratios in the chemical equation for moles because they are both counts. This 2 is telling me that that's the number of C2H6s I need, and the 7 here is the number of O2s I need. And again, 13.9 is just a count, the same way anything else is. So what I'm going to do is I'm going to set up my ratio. C2H6 to O2. Always whatever you're given something about, and always what you're requiring to solve. Notice that I haven't even talked about CO2 or H2O. They're not part of this question. I don't need them. Now, obviously, I need them in order to balance the equation, but I don't need them in order to solve this. So now I go to my chemical equation and look, 2 goes with the C2H6 and 7 goes with the O2. That's the numbers you need. So then I come over here and I say, well, I've got 13.9 moles of the C2H6. How many of the oxygens? Okay, so I basically got to solve this ratio. So let's do some cross multiplying. I'm going to multiply that up, and I'm going to say 2x is equal to 7 times 13.9, and then divide by 2 to get x by itself. So go to your calculator. 7 times 13.9 equals 97.3 divided by 2. I'm going to need 48.65 moles of the O2. That's how much of the O2 I'm going to need if I have 13.9 moles of the C2H6. Okay, cool. Let's try another one. How many moles of the, I'll change color pens here, how many moles of the H2O? So now our question mark is over here. How many moles of that would be produced by 1.4 moles of the O2? So look at this now. I've been given N is equal to 1.4 moles. Okay, well, let's set up our ratio. I'm given something about O2, and I'm trying to solve something about H2O, so I'm going to put them down. I'm going to go to my chemical equation and write the numbers. So I know 7 goes with O2 and 6 goes with H2O. But I've been given that I've got 1.4 moles, not 7, 1.4, and I want to know how much of the H2O is going to be produced. Great. Well, let's cross multiply. So 7x is equal to 6 times 1.4. and then divide by 7. All right, so 6 times 1.4 divided by 7, and we get x is equal to 1.2. So if you have 1.4 moles of O2, you will produce 1.2 moles of H2O, and it kind of makes sense. Because look, it's a 7-to-6 ratio from our balanced equation, so it's a little, you make a little bit less of the H2O than what you started with of the O2, and sure enough, it's going from 1.4 down to 1.2, so the numbers make sense. Okay, let's try one more question here. It says nitrogen can combine with oxygen to form several different oxides of nitrogen. These oxides could include NO2, NO, and N2O. So this question, they haven't given you the balanced equation, you've got to write it. So the first question is, how many moles of O2 are required to react with that big number of N2 to make N2O? Well, the first thing we're going to have to do is write our equation. So here we go. For A, we've got O2 combining with N2 to form N2O. Okay, so let's write our equation. I need to balance this. That's the first step. So look at this. I can see that I'm going to have to put a 2 here because I need 2 oxygens on this side. So I put a 2 there to get the 2 oxygens. But then I noticed that I'd need a 2 here. And they're often pretty easy like this to balance, so I didn't do the whole listing of them. But basically, this tells me that 1 oxygen gas molecule plus 2 nitrogen gas molecules makes 2 of these dinitrogen monoxides. Okay, well now what it says is how many moles of O2, so the number of moles is the question mark, is required to react with, and look, I've been given here that I've got 9.35 times 10 to the negative 2 moles of N2. Now, a lot of you can probably see right off the bat what the answer is. You probably don't need to do the whole ratio, but I'm going to do it anyway. So look at this. I'm interested in O2 and N2 because that's the one that I'm asked to solve something for and the one I've been given something for. I'm told nothing about the N2O. So watch, I look at the equation and it's a 1:2 ratio. Here's my unknown, it's the number of oxygens, but I've been given 9.35 times 10 to the negative 2. So I've got to cross multiply. So I'm going to cross that up here. Now, when my unknown is on the top, notice that I don't really want to bring the 2 up because that's just going to get in the way. So I'm just going to leave it. So look at this. It'll be 1 times 9.35 times 10 to the negative 2 divided by 2 is x. Just, again, I want to emphasize here the reason why I didn't cross multiply the 2 up to the x is that it was already on the right side. So really, my answer is just 9.35 times 10 to the negative 2 times 10 to the negative 2 divided by 2. And you get, my calculator says x is equal to 0.04675 moles, which is just half, obviously, of the 9.35. And a lot of you might have said that to begin with. You said, well, if it's a 1:2 ratio, I need half that amount of the O2. And you were right. Okay, let's do one more here, and that is this one. It says how many moles of O2 are required to react with this 9.35 times 10 to the negative 2 moles of N2 to form NO2. Well, this time then, we've still got the O2, and we've got the N2, but this time we're making nitrogen dioxide, so now we got to balance it. So right off the bat, I would see that I need 2 of these to match up with the 2, but then I would have 4 oxygens, so I'd need a 2 here. So it's a slightly different balanced equation. And now look, it's asking me how many moles of that would I need to react with. In this case, it's the same number, but we're going to get a different answer because we've got a different balanced equation. Okay. So here we go. Let's set up our ratio again. It's the same 2 compounds, N2 and O2. But in this case, it's a 2:1 this way ratio is equal to x over 9.35 times 10 to the negative 2. So we cross multiply. So look again. I can just multiply that up there. 2 times 9.35 times 10 to the negative 2 divided by 1. And so it's going to be 9.35 times 10 to the negative 2 times 2 equals 0.187 moles. Okay, so today's lesson was all about using these ratios, pulling the ratio from the balanced equation and using that to determine some other count that we require. I've put your homework questions on this on the file, and I've put the answers here. Please give those a shot and let me know if you have any questions.